So hello everyone, welcome back to 3 Deviations. In today's video of single variable calculus, we are going to be covering the fundamental theorem of calculus part 2. So if you remember, if you watched the last video, we talked about the fundamental theorem of calculus part 1. And at the end, I said that I was really excited to talk about this fundamental theorem of calculus because I think that this fundamental theorem of calculus is probably one of the most helpful theorems that we are going to have in calculus. This is going to be your lighthouse for basically the rest of not only single variable calculus, but multivariable calculus as well. If you are doing calculus and it involves an integral, you will be using the fundamental theorem of calculus. It's almost certain. So more specifically, actually, the part 2, this is the really important part. This is what's going to be universalized. This is what you're going to be using on all your tests and all of this. So it's really important. Right, so that's my shtick about how important the fundamental theorem of calculus is. Now I think we should probably just talk about a quick prerequisite. Anti-differentiation is something that is going to be required for this video. Nothing too complicated, just the reverse power rule, integrals of, or antiderivatives of sine, cosine, ln, e to the x, all that stuff. But just note in the future, in Unit 4, coming up soon, we will be just covering some more anti-differentiation before we move on to some more applications in Unit 5. All right, so let's cover the fundamental theorem of calculus part 2. So what the fundamental theorem of calculus part 2 deals with is integration. So up to this point, what we have been dealing with is we have been dealing with the integration by Riemann sum. So what we've said is we've said that if I take the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. And we said that that is equal to the definite integral between a and b of f of x dx. Right? And when we've seen this here, we usually need to revert back to this so that we could find our actual value for what our area under the curve is. Now, from this point on, once I mention the theorem, we are going to be using this almost every time. This is going to probably leave your heads for a while. Although you probably still will need to remember this. If somebody comes up and asks you, or more likely your teacher comes up and asks you, what is the formal definition of the integral? Well, you're going to need to say that it's the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. But we just like to write it here when we're just evaluating some integrals. So as we remember, evaluating those integrals was not fun at all. We needed to deal with those Riemann sums. We need to deal with the sigma notation. We could not even imagine how hard it would be if we needed to integrate these functions or find the area under a curve of some more complicated functions with those Riemann sums. Out of the question. It's very tricky to do. But we're going to fix that now with the second part of the fundamental theorem of calculus. So here's the statement. It says, let's consider a function f on the interval ab. So if this function is continuous, then we can assume the following. So the following says that the integral from a to b of f of x dx is equal to the antiderivative of the function little f of x evaluated between a and b, which just means we're taking the antiderivative, evaluating it at b, and then subtracting the evaluation at a. And as I said earlier, f is going to be the antiderivative of little f, such that capital F prime of x is equal to f of x. So if I have capital F, if I have f prime of x, if I have f of x, I have capital F of x, and I differentiate it, I will get little f of x. And if I anti-differentiate little f of x, I get f of x, big F of x. I'm going to rewrite the second part of the fundamental theorem of calculus in a way that I think more replicates the connection between the derivative and the integral. I'm just going to write, instead of little f of x, I'm just going to do capital F prime of x to show that that's the derivative of the function that we're evaluating, just so that that's clear. When I evaluate an integral, what I need to do is I need to find the antiderivative of the function inside of the integrand, and then I need to evaluate that at both a and b. So that's how, and then I subtract it. So that's how the fundamental theorem of calculus part 2 works. Now, as you can imagine, taking those antiderivatives for the elementary functions is really easy. We talked about a table back in video 40 that we could revert back to, and that I hope you memorized, that you will remember those integrals. But don't worry if you are thinking, well, what if there are more crazy functions that I need to anti-differentiate? We're going to be devoting units to that in the future, but that will be covered later. All right, so now that I've thrown all of this kind of abstract information at you, why don't we do an example? So we are going to try integrating e to the x from 2 to 4. So to do this, I need to determine the antiderivative of e to the x. Well, what function's derivative is e to the x? Well, it's just e to the x, because e to the x is infinitely differentiable and it just stays e to the x. So our antiderivative is going to be e to the x. So now I need to evaluate that between 4 and 2. Or 2 and 4, sorry. So we're taking the integral between 2 and 4 of e to the x dx, and that's going to be equal to e to the x evaluated between 2 and 4. So I take e to the 4, then I take minus e to the 2, and that is our final answer. We have an exact answer for the area under the curve between our intervals. So, right, this is roughly what e to the x is going to look like. So, probably not to scale, but if I have 2 here, I have 4 here, so I'm taking from 2 to 4. E to the 4 minus e to the 2, that's the area in there. And that literally took seconds, as opposed to literally we filled the whole slide up with summations and limits, and it just got all messy. This was so clean. That is why the Fundamental Theorem of Calculus Part 2 is so nice. All right, now let's try another example. So this one will require us to do a little bit more thinking about what the antiderivative is. So we're going to take the integral from 0 to 1 of x squared dx. So we need to find the integral, or the antiderivative, of x squared. So if we remember back to Unit 40, we had what we called the reverse power rule. So it basically allows us to take the antiderivative of the power functions, or of the monomials. So if I have f of x, if I have f prime of x equal to x squared, then I can plug it into this reverse power rule, which says if I have a function x to the n, and I want to anti-differentiate it, well, that's just going to go to x to the n plus 1 over n plus 1. So I like to separate this into a little bit of a fraction here. So we just get f of x, capital F of x, is equal to 1/3 times x cubed, right? So we're raising the power and then we're dividing it by n plus 1. All right, so that should be pretty easy. So now that means that the integral between 0 and 1 of x squared dx is equal to 1/3 x cubed, evaluated between 0 and 1. And that's going to be 1/3 times 1 cubed minus 0, which is just 1/3. If you remember, we dealt with this earlier in one of our first videos on integral calculus, seeing if we could find the area underneath x squared between 0 and 1. Again, it took us quite a long time, but now we found that this area is just equal to 1/3. And again, it took seconds, just like the when we did the last time. That was pretty easy. All right, let's keep going. This is fun. So we are going to try integrating between 1 and 5 dx over x. So I can separate this, and this can become the integral between 1 and 5 of, can take 1 over x dx. And so now I need to think, well, what function has its derivative 1 over x? Well, that's a special case. We have the natural logarithm of x gives us 1 over x when we differentiate it. And a side note that we did talk about in video 40, we need to add these absolute value bars around when we talk about the antiderivative of 1 over x. All right. So now we've found our antiderivative. So now we need to take the integral from 1 to 5 of dx over x. That is just going to become the natural logarithm of the absolute value of x, evaluated between 1 and 5. So this is going to be ln 5 minus ln 1. ln 1 is 0, so that just becomes ln 5. All right, so now that we've covered that, we're ready to move on to anti-differentiation, and that's what we'll do in the next video. Bye-bye.